Okay, chapter 15 was basically all just learning rules for derivatives, and there was a lot of just drill and practice and practice and practice, okay? And the reason why that's important is because before we can apply derivatives to anything, you've got to be able to find the derivative first. So we're going to be spending our time here in chapter 16 and 17 looking at various applications, and there are a lot of applications. We're going to look, particularly in chapter 16, is focused on curve sketching. When you did in year one, when you did some stuff with parent functions, you recognized how to find zeros, and you could approximate where a max or a min point would be based on where your zeros were, but you couldn't actually find them yet. And then the rest of the graph was just kind of, eyeballing it, or it's somewhere around there. This is kind of what it looks like. Well, what we're going to be doing here is using derivatives to find various features of our graph and also relate those features to motion or to various applications. So chapter 16 focuses a lot on that curve sketching, and then chapter 17 does a lot with optimization. For example, this is a model. What value is going to give us our best solution? So we have a number of different things in that we'll look at as well. Okay. Now we're going to practice a couple of finding equations of tangent lines. We did do this in the last chapter a little bit, but I want to do a couple here, and then we're going to use the same two functions as we look at other applications throughout the day. But first of all, let's take a look at this diagram here. First of all, you'll notice we have this point A on our function y equals f of x. And point A has an x coordinate of A, and then notice this is f of A. Now that may seem a little elementary at this point, but notice you're plugging the value for x into the original function. As we do these applications, not just what we're doing today, but all of the applications, one of the most common mistakes students make is when they're trying to find a value of the original function, they accidentally plug the value of x into the derivative instead. Okay? Anytime you're looking for a point on the original function, make sure you plug your x into the original function. Alright, so I just wanted to mention that right at the beginning, and I'll say that numerous times throughout the chapter here. But this point here is our point of contact. You could also call that the point of tangency. I'll probably call it that more often than I'll call it a point of contact. But we found this tangent line whose slope or gradient, we're going to use m sub t, that's a capital T next to it. It's the slope of the tangent line. There's nothing special about that notation, it's just, in this case, distinguishing the slope of the tangent line from the slope of this line right here, the normal line. Okay? We're going to use m sub n for the slope of our normal line, as you'll see here in a moment. Okay? But I want to introduce why this normal line is significant. All right? When calculus was first being developed, there were a couple of basic problems that Leibniz and Isaac Newton were both trying to solve. Okay? They lived there at the same time. Newton made some discoveries and invented calculus, so to speak, or discovered calculus. First, chronologically, but Leibniz didn't really have any contact with him. They knew that each other was studying this concept, but Leibniz, not knowing what Newton had discovered, about, I think, a decade or so after Newton, came up with many of the same things. And actually, he's the one that developed the integral symbol and a lot of the other notation we use today. But they are both considered to be kind of co-discoverers of calculus because Leibniz was the first one to publish and make his findings known to the public. Newton was the first one to actually do it, but he didn't tell anyone about it, except just the couple of people that he was working with. So they are kind of recognized as being the co-founders of calculus. But a couple of the questions that they were looking to solve, one was the area underneath a curve, the area bound by a curve, and that's actually what we find by when we're doing integrals. But the other one is actually not the tangent line, but trying to find this normal line. And the reason why they were trying to find the normal line is because back then especially, there was a lot of study being done in the field of optics. In the field of optics, okay? And in optics, one of the basic rules, you know, optics is working with lenses and mirrors and that sort of thing, okay? You guys talking about your contacts, all right? A lot of that research was done, okay, back at this time. You know, the forerunners of glasses and making telescopes to be able to see out into space and whatnot. Development of those lenses. One of the basic rules is that the angle of incidence, which is an angle, if these are light waves or whatever coming at the surface, this would be our angle of incidence, and that's going to equal the angle of reflection, okay? And those angles are measured as an angle from the normal line, okay? So obviously, in order for them to advance their study of this, they had to be able to find what that normal line was on a curve. They recognized their lenses were curved surfaces, so they had to be able to do it on a curve. So kind of an interesting study there, but that's kind of what sparked a lot of this delving into the math and trying to find derivatives and that sort of thing. Okay, so that's why this normal line is so significant, because it really is at the foundation of why calculus was developed in the first place. So let's take a couple moments here and let's practice finding the derivative, the tangent line, the equation of the tangent line at a specific point. So here I gave you two functions here. One is a parabola, and this parabola looks something like this, okay? We want what the slope would be at x equals 2. So in other words, we're looking at, let's say x equals 2 right here. What's the equation of this line? Okay? Okay. What are we going to use the derivative of this to find?
The slope of the tangent line.
Exactly, the slope of the tangent line. So, if I want to find the slope of the tangent, I need to first of all find the derivative of this function. What is the derivative of this function?
4x.
Okay, yeah, negative 4x plus 1 or 1 minus 4x, either way you want to put it. Okay? And then I'm going to evaluate that where x equals 2. Okay? So when x equals 2, 1 minus 4 times 2, 1 minus 8, our slope is a negative 7. Okay? The other thing I need is a point. What point am I actually going to be tangent at? The contact point. Well, I know it's 2 something. So what am I going to do?
Point slope.
Okay. that's how we'll get our equation, use point slope form.
Or you just plug 2 into the original equation.
To get the y coordinate, we've got to plug 2 into the original equation. Alright? So 2 minus 2 times 2 squared plus 3, that gives us a negative 3. So that's the point that we want this to hit. Okay, so obviously my drawing is a hair off. This thing should be down here. Okay? There we go, that looks a little more tangent. Okay? So there's my point 2, negative 3. Okay? Now, you can use either y equals mx plus b, or you could use the point slope form, whichever way you want. At this point, finding the equation of a line should be a no-brainer for you. So you just work your way through doing that, okay? You use point slope form, x minus negative 7 times x minus 2 equals y minus a negative 3. Okay, negative 7x plus 14. So y equals negative 7x plus 11. That is the tangent line. And if you look at it, it makes sense. Alright, it's going down pretty sharply, and it's going to hit somewhere way up here. So that is at least a reasonable answer. Okay? Does that make sense? Alright, good. Now let's take a quick look at B. Let's get our slope, make sure we all get our slope properly, and then I'll let you take it from there. Okay? First of all, I want the equation of the tangent line to y equals the square root of x plus 1 at x equals 4. So the first thing I need is dy dx. And what is that here?
1/2 x.
Yeah, 1/2 x to the negative 1/2. Or, if you will, 1 over 2 root x. Now the nice thing with these applications, guys, is that it doesn't matter how much or how little you simplify. Okay? Now it may be a little more challenging to evaluate if you don't simplify, but it's kind of up to you. Unless you're specifically asked for the derivative first, and then you're asked to apply it later. If it's just in the midst of a problem, you're welcome to leave it like this if you want. Okay? Because really all we care about is then the value. So what is the slope of our tangent line in this case?
1/4.
Yeah, it's 1/4. You plug in 4 for x, and it's 2 root 4, 1 over 2 root 4, which is 1/4. Okay? So take it from there and find your equation. If you have a question, I can answer that. It's just like a period. Some people finished a little bit early, and everyone finished within lunchtime.
I was thinking Wednesday, like 25 minutes period, and then go
Yeah. Square root of 4.
So
just 3.
Y minus y1 equals n plus 1.
2.
So 1.
Yeah, I mean, we didn't do much in the past years, and like now it's just,
Y.
but, that was,
That's fine with me, let me know.
That's not what they're asking today.
Yeah, at least ask them if
That's
they know it's
fine.
Minus
that would be fine.
Okay, thank you.
Y minus square root of 4.
That's why, well, I was looking for that.
Alright, so what'd you guys get?
X over 4 minus 1, or sorry, plus 2 equals y.
What'd you get? Plus 2?
Yeah.
Okay. Once again, we need to find the point that we're going through. So if you plug in 4, you're going to get y equals 3. So our point here, our point of contact or point of tangency is 4, 3. Okay? So you plug the 4 in for x, you plug the 3 in for y, and you get 3 minus 1 is 2 for b. Okay, so y equals 1/4 x plus 2. Does anyone not get that or not see how to get it?
Can we quickly just do it?
Do you like using point slope form or do you like just using the y equals mx?
Y equals
Okay. Yeah, if I'm using y equals mx plus b, what I'll do is I'll put 3 in for y, my slope in for m, the x coordinate 4 for x, and then I have to solve for what b is. Okay. So 1/4 of 4 is 1. So obviously then b would equal 2. And then I just put my variables in my m and b in. Okay? It may have been a while since you guys did equations of lines, so that's alright. Alright, so there are our tangent lines. Let's go back here now. I want to look at normal lines. We said normal lines are perpendicular to tangent lines. How are perpendicular lines related?
They have the negative reciprocal slope of the line that they're perpendicular to.
Yeah, okay. Perpendicular lines have negative reciprocal slopes. So, if I know the slope of the tangent line here is -7, what is the normal line at x equal 2 going to have for its slope?
1/7.
Yeah, positive 1/7. Okay, let's take a look here, just so you can see it all. The normal line is the perpendicular to a curve at a point. It's perpendicular specifically to the tangent line. Okay, the gradient or slope is this m sub n. Okay, or if you want, you can put, I'll write that sometimes, just so I remember it's perpendicular. Okay, the slope that is perpendicular to the tangent line. But you see here the negative reciprocal. -1 over the slope of your tangent line, that f prime of a. Okay. So, these are the same functions we found the tangents to. And notice the point of contact is still going to be the same. Alright, but now we had this. So when we bring it over here, we have the point, we have the slope of the tangent line. So, like we said here, the slope of the normal line is a positive 1/7. Then it's a matter of finding the equation again. Okay? So again, whether you use point slope form or slope intercept form, you plug your values in and you can find your equation. Alright, so you find out whatever B is. And you guys have a value for B?
Just plug in negative.
Plug in your -3 for Y.
Negative 23 sevenths.
-23/7, yeah. Okay. That's 2/7, you subtract that from both sides, you get a -3 2/7, which you can leave that way, or like Andrew said, you can make it a -23/7 if you want. So here's our normal line, y equals 1/7 x minus that 23/7. Okay. Now, if we have the equation of the object, remember we talked about the angle of incidence and angle of reflection. Now that we know the equation of our normal line, if we have an equation that models the path of the light or whatever it is that's bouncing off of our curve, we can take those two slopes, make them into vectors, use those vectors to find the angle between the two vectors, and now we know what our angle of incidence is, and we can then calculate what the angle of reflection will be. And there might be an easier way to do that even that I'm not thinking of, but that's one way you could do it. Okay, but there's our normal line. So try this one. I'll put up what we had before. I'll just go back. Okay. Here's what we did for the tangent line. Go ahead and find the equation of the normal line. They're at x equals 4.
The points are gonna change. So let's find the point first. Is that y is changing or the slope is changing? So plug 4 onto the original. What did you get? Oh, so. Finish the Negative 4.
Oh, it's negative.
Four, 3. And what's 16? What's 3 minus 16? Negative 16. B is negative y equals 4x minus 13. You follow me?
You don't really say things, you just kind of do it in your head, and you say like random bits and pieces. I'm so sorry.
No, we're asking you finance. So what are we doing for last week?
Alright guys, what'd you get for the slope? -4, good. And then, yeah, make sure you make it the negative reciprocal, not just the reciprocal. Okay? And then what you get, it's going to be y equals -4x plus 19. Okay? Plus 19. If you plug in the 4 here, you get a -16. You plug the 3 in here, and then you add the 16 to both sides, you get 19 for B. So there's our normal line. Okay? Any questions so far? Alright, good. Now, we have tangent lines, we have normal lines. Now I want to look at particular type of tangent, and that is when the tangent line is horizontal. Okay? What do you know about a horizontal line? The slope is 0. So the slope is 0, so we need to find where the derivative equals 0. That's the key to this whole part. Now, probably in this chapter 16, there's probably no more significant application than this right here. Okay? These values that we're going to find that make the derivative equal 0 are what are known as critical values. Okay? Your book has another term for them too that I can't remember off the top of my head, but they're more commonly known as critical values. These we're going to use to find max and min points. We're going to use these to find optimal solutions to problems. You know, a number of different things. So, notice here I eliminated at a specific point because we don't know where this is going to occur. But let me ask you something. On this parabola that we've been dealing with, looks like this. Where are we going to have a tangent line that's horizontal? Yeah, it's going to be at the maximum, okay? Over here, you know, it's going to be going uphill. Over here, it's going to be going downhill. But right at the maximum, we're going to have that horizontal tangent line, okay? So like we said, we want to find where this derivative will equal 0. So again, we have our derivative, which was 1 minus 4x. So if that equals 0, what is x going to equal?
Oh, sorry. 1/4.
There we go. No, you were right the first time, 1/4. So we'll subtract the 1 and get negative 1, divide by negative 4, and we get a positive 1/4. Okay, so guys, that tells us where our max point is going to be, at least from left to right. It's going to be at x equals 1/4. But then, how are we going to figure out what that horizontal tangent actually is? It's going to be the equation y equals something. How do we find that?
Do you plug the x equals 1/4 into the first equation?
Yes, plug it in. We're finding an actual point on the graph, right? So we need to plug it into the first equation. If we plug it into our derivative, what are we going to get?
0.
0, because that's how we got the 1/4 in the first place. We set it equal to 0. So hopefully if you accidentally do that, you'll notice. But you plug it back into the original function. We now know that y equals 1/4 minus 2 times 1/4 squared plus 3. And if you work that out, you're going to get 3 1/8. Alright, so that actually is the equation of that horizontal tangent. We also now know the max point on this parabola is the point 1/4, 3 1/8. Okay. Alright. So, if we were trying to sketch this parabola, here's, 1/4, here's 3, which actually is our y-intercept. But that would be 1/4, 3 1/8.
Mr. Dixon, won't the 2 times 1/4 squared cancel out because 1/4 squared is 1/8? And then if you multiply the top by 2, it's 2 over 8, which is equal to 1.
Well, no, 1/4 squared would be 1/16,
Oh, whoops.
not 1/8. Yeah. All right. Any other questions here? All right. Now let's think about part B. dy dx equal to what? Well, it was 1/4 when x equaled 2. But what did just dy dx equal?
0.
1 over
2x.
2 root x. Okay? Where it was 1/2 x and negative 1/2. Right? So 1 over 2 root x. Where will that equal 0? Do you know what this looks like? It'll be undefined if I plug in 0. This is going to look like this. Okay? There's an asymptote at y equals 0. Okay? Now this is not the graph of this. This is the graph of my derivative function. Okay? So when will this equal 0? It won't. Alright? So, are there any horizontal tangents on this? No. Hey guys, this is where knowing your parent functions is helpful. Okay? If I'm graphing y, remember the square root of x starts at 0 and goes up and continues to go up. This, since it has a plus 1, it's going to start at 1 and it's just going to look like this. Right? So, this was y. If I'm sketching my dy dx, if I'm sketching my dy dx, it's going to look like this. Okay? It's never actually going to equal 0, which makes sense. If we look at this, it's never going to have a peak. It continues to go up and up and up forever, right? So that makes sense on that one. So this one has no horizontal tangents. Okay.
But does that not follow the rule? If it's if the degree is larger on the bottom, then it's well, the degree on the bottom is 1/2, and the degree on the top is 1.
Oh, the degree on the top would be 0. So it does theoretically, as we approach infinity, as x approaches infinity, the value of this approaches 0, but it doesn't actually equal 0, ever. Okay? Alright, so we have tangent lines, we have normal lines, we have horizontal tangents. The last thing I want to look at is really just a kind of a special case of our first, finding a tangent line. And that is finding the tangent line when our original function is a logarithmic function. Okay? Now some of you have struggled a little bit with logarithmic functions. Let's jump to step 2 for a moment. If I'm finding the slope of the tangent at this point that we haven't found yet, first of all I need to find dy dx. What's the derivative of the natural log function?
The derivative of that.
Yeah, it's 1 over x. Okay? The derivative of natural log is 1 over x. If it were, say, the natural log of x squared, remember, oh, not equals.
It's the derivative of the inside over the
Inside. Yeah. This is where on the worksheet that you guys did, as well as those who took the test, this is kind of a common problem I've seen on homework and on this stuff. You're wanting to keep the natural log in your final answer. Okay? When you're taking the derivative of a natural log, there are no natural logs in the result. Okay? It would be 1 over what you're taking the natural log of, and then you use the chain rule, so it's times the derivative of what was inside your natural log. Okay? So in this case, it would be 1 over x squared times 2x, which of course the x and would cancel out one of those in the denominator, so it would just be 2 over x. Okay, but notice there are no natural logs in our result for these logarithmic functions. Okay?
Would it not work properly if you didn't use the chain rule? If you just went right to 2x over x squared?
Well, if you're doing 2x over x squared, you are using the chain rule. You're just kind of putting it together right away.
Because I remember how I thought of it, just the derivative of it.
Yeah, and that is the rule our book gave us. I just wanted you guys to make sure that you understood that rule was the chain rule. Yeah. Okay. All right, so we'll get to actually finding what this slope is in a moment, but the point of contact when y is -1, okay, this makes it a little more challenging. -1 equals the natural log of x. How would you solve that equation? Yeah.
You raise it to the e raised to. You gotta use an e to get rid of
-1 is the exponent of e that gives us x. So x is 1 over e. So when I plug that in down here, my slope is e. Then I can plug that in and I can figure out x minus 1 over e. And y equals ex.
Like we all know exactly what
Right, minus
It takes constantly.
Ronnie, what are you?